Okay, so I should also just played around with this a bit. I should be able to read the Zoom chat here as well. So yeah, we can see it there, but it's on this one here for me. So for a lot of this tutorial, there'll be big kind of blocks of code in kind of sections like this, segmented out. For a lot of these, we can basically just copy paste things directly. So in terms of demonstrating things, I'll be doing a lot of that, where basically I'll take some of the code, drop it into my window on the other side in the terminal, and we'll see what happens when we run it. Here we're talking about basically grabbing some files. This needs to be done with an EIC shell. We'll talk about this in a little bit more in a second. But as I say, that's effectively all we're actually going to need EIC shell for in this first bit of the tutorial. Okay, so I'll get started. So this tutorial, as Holly kind of started and introduced very nicely, there are a lot of distinct use cases in terms of what people want to do with the Epic software. This is very much the kind of one extreme in the sense that a lot of that chain we saw in terms of, running some simulation, even generating a file, all of that is already done. And we're looking at the very kind of last step of that chain where we're looking at the output of the reconstruction and we want to analyze it. Typically, this would be, for example, if you want to look at a specific physics process. I know that's a lot of what's happening in terms of the physics working groups now, where for the TDR, we want to make certain plots, look at certain properties. If you're jumping into a task from a physics working group, this is maybe the best point to start, where we maybe want to look at a certain channel, look at some reaction where there's already some files to look at and run and process, basically, and try and get some results out. So in terms of getting files, and identifying what we want, that's the first kind of topic of this, is just where can we get the files, where can we download them, how do you browse them, and what sort of things are there. So as I say, this very much is the only part we'll actually need EIC shell for. So if you can't get it running or you have problems getting it running still, apologies, but once you do, try this out, come back to this and have a look and start trying to explore the directories and see what's there. Because in terms of actually doing your own analysis, analyzing a specific physics process, you're of course going to need your own files to take a look at. So we'll take a quick look at that. A lot of the information here is quite condensed. If you want to look at specific details about the production campaigns, all the stuff presented below is on the website, so in this link here, just take a look at that, see what's there, and they'll have a kind of more detailed explanation of this as well. But in terms of how things are organized, I think Holly's already briefly touched on this as well. Broadly speaking, there are 3 different classes of files that we might want to look at and might want to browse. Event generator level stuff. So this is very much if you were creating an event generator or running some event generator, these would be the output files from that, and they're basically the first step of that production chain. In terms of validation, you might want to go back and check, are you actually seeing what you're originally putting in from your event generator? So if you were someone that was making some new event generator and putting in files, that's where they'd be, and you can go and take a look at that. Whereas the full directory, which basically is the kind of quote-unquote full Géant 4 output, this is the output of the simulation. So if you're running the simulation yourself and you had kind of all detectors turned on, stop sharing for whatever reason. Yeah, and typically for the simulation campaigns, they don't run everything as a full simulation. But if you were kind of running the simulation yourself, if you're doing a full chain, this would basically be your output from npsim. You run a particular detector configuration, get something out from that. That's what you get. So this is basically the DD4 HEP output files and things like that. And finally, the part where we're going to be looking at Reco. This is basically the output files from the reconstructions. Once you have those simulated events, they're passed through the reconstruction, through EIC Recon, and depending upon the factories and algorithms you turn on, you're going to get different output from that as well. So in terms of if you're doing just a physics analysis, effectively it's only this one here, the reconstruction, you're really going to be taking a look at and playing around with. You might want to take a look back at these eventually, for example, for validation though, and again, checking that it matches what you originally thought you were putting in. Within each directory, things are organized by campaign, as we saw. So year, month, and then the run. So in this case, 2312 would be last December, the first run of that. And also then within that, they're kind of sorted by detector configuration. So epic crater lake, for example, particular configuration of the detector, and then physics process. So this step basically is broken down into each of the physics working groups. So you can quite quickly, for example, if you were looking at something in the inclusive working group, you could just look into the inclusive files, see what's there, try and grab what you want to get. And then within that, they're broken down by further subdirectories, so generator version, the energy, Q squared, and so on, as we saw. The full structure and kind of details there, and also Holly outlined that as well. Okay, so first step, accessing the simulation files. So for this, this is the only step where we actually need ESC shell. So wherever you are, you can basically hopefully have some working version of ESC shell. So in this case, I'm on the Jefferson Lab farm. And do a quick LL, we can see ESC shell is there. So hopefully when we run that, we'll do something. After thinking about it for a bit, it will. There we are. So once it's up, we have this drug Excel, blah, blah, and we see where we are sitting inside there within the ESC shell. And now hopefully we can run all of these other commands in terms of what's there. So I'm just going to clear that, and we can run our next step. So in terms of browsing those files, we can use XRDFS with the server. So we can go ahead and type that in. Again, after some thinking, we're now on that server, and we can browse around there and see what exists. So this ls line, a kind of typical command in terms of browsing file structures in Linux. Plug that in, see what's there. So in this case, we're looking in specific directory, EIC2, and we're looking at reconstruction. So again, we've skipped straight away to the reconstruction where we're not looking at, for example, full. We could go back and take a look at that and see what's there. So type that, we'll see what's inside here. All we have is that inside there is epic crater lake. So that's our only detector configuration for this particular simulation campaign. We can then go and take a look inside that and see what we have. And indeed, there, as discussed, we basically have within that all of our different physics processes. So, I don't know, just as a random example, because what I'm interested in, we have a look inside the exclusive directory, we'll see what's there. We see that there's I didn't here, I don't think. Yeah, it doesn't tab autocomplete, unfortunately, within it does in this. Within XRDFS, it doesn't, which is actually quite annoying. So the question in the room was what I was using for tab autocomplete. I was actually just hitting it lucky and typing it correctly first time because it doesn't tab complete within this, which is a bit unfortunate. You could also just copy paste the line as well each time if you like, since once you've done the LS. But yeah, within this we see basically all of the different physics processes. Again, for no particular reason other than it's what I do. We'll take a look at this directory. We see there's a particular generator version. And then within that, we see there's different beam energy combinations as well. And I guess for completeness, let's have a look at what's inside one of those. Within that, we have then different sub-processes. What's your favorite? Meson, I guess, Pion. And then within that, we have all of our files. So we see there's a huge load of output files within there. And if we like, we could then go and grab one of those as well. But for now, we're just going to exit and clear all of this junk off the screen. We can also copy files. So once we identify the file and which one we want to grab, we can go ahead and copy something out. So that's what we'll hopefully do next. So again, within the EIC shell, I'm not going to run that again. I'm already there. I could then just say, OK, let's grab one of those files. But in this case, we don't have a path to file here, so it's not going to give us anything. But we could go and plug in, for example, again, for no reason other than that, it's what we want. We could go in and put in the rest of that there as well, and it will hopefully download a file for us. So this last little comment here, this little dot, that's just saying copy that file from that directory and put it wherever we're running this. So in this case, it's going to dump it to this path. Go ahead and do that. 33 megabytes, relatively small. So now if I do an ls, hopefully that file will be sitting there. And indeed it is. We have this data file that we're going to need. So that's one way of looking at it, and hopefully people have had some success with that. Have a try, have a little bit of a play around, or maybe give people 2 or 3 minutes, just have a little bit of a browse, pick out their favorite physics process and start taking a look. And for the example and for the rest of the tutorial, we're going to be analyzing a file. So grab one of the files from this directory. It doesn't need to be 001. You could grab 002 or whatever else is in there to take a look at. So you can go ahead and grab a file. Each of them should only be about 30 megabytes or so, so it shouldn't take too long to download. We'll take another look at a different way to do this as well, so you don't necessarily need to copy it now. Just have a little bit of a browse and play around and see what's in there as well. And I guess a disclaimer, we're going to be using a slightly older simulation campaign file. The only particular reason for this is due to a root version issue, which we'll discuss in a second, but in this case, in terms of analyzing, it doesn't really make a huge difference. Maybe the names of some branches will change slightly or something like that, but that's all that's really going to affect. If you're grabbing other files, some of them might be a bit larger or smaller than this one as well, but in terms of the tutorial, we'll be using one of these files. So, I mean, you could use something else, it's just that it might not necessarily make sense in terms of the output that you get from it as well. Or at least it won't look like everyone else's output if you get something else. All right, everyone browsing happily? Any issues, anything like that? If you're having any problems, just post them in the Mattermost or in the Zoom chat, and we can hopefully try and answer or address those. Of course, if you had trouble with EIC shell, apologies, this section isn't going to be useful at the minute, but do come back and take a look at this and have a little bit of a play around and take a look what's in there. Okay, so as an alternative to this, we can also use a slightly different approach where we can use this mini client and then mini IO client. To get that, just follow these steps. Again, do this within EIC shell. So if you're within EIC shell, you can go ahead and run all of these. You can copy paste all of them straight into your terminal and should hopefully run and work fine. Like I'm presenting some sort of kids art show, I've already done this, so I can go ahead and run it, which I'll do in a second. However, if we copy paste this command, there's something critical missing here in terms of the config. So we need to put in a credential and another credential. So this is the fun part for people who are responding on Mattermost. If you want to do this and set up this config, just please ask for the credential there. How secret is this? Can I post it in the Zoom chat? I already posted it. Okay, cool. Yeah. Okay, so it's not so secret and isn't exactly the most surprising password or credential ever. We'll go ahead and plug that in. So where it says credential in the kind of inside the, I guess, the quantum mechanics style brackets almost, inside these things, if we plug in that, you should be able to then set this config up. It will take a few seconds, but once you've done it, you can then run this command at the bottom. So I'm going to go ahead and do that. Can run this, and again, we see with this ls command, in this case, we've actually gone a few levels down, and we're just saying, okay, what is there in terms of the reconstruction? And we see that this huge list of campaigns is available there. So again, year, month, and then version of the campaigns. We see stuff stretching back to October 2022. We'll also just see what's there in terms of things. So again, of course, we see event generator, full, and Rico as well. So we could look in, for example, full. Let's plug in a more recent campaign, so March 24. You don't need to fully qualify full/bin/MC, but MC should be installed inside the shell. So we can just do MC. Yeah, so we just do mcls. Yeah. And see what's there. Yeah, cool. And again, we could do within that, let's just pick a simulation campaign. Let's do that. And we'll again see, in this case, we actually have two different detector configurations we could look at there as well. So again, we can browse that very much like we did the other one. In this case, we don't have the full range of physical processors, but we could jump in whichever of these we want and start seeing what's there in terms of the files. So just a different way to do it. And of course, if you replace ls there with cp, I'll maybe add, oh, actually, whilst I'm there, I'll maybe mention. So as Holly mentioned, all of the tutorials that we're running here are based off of GitHub. So I'm just going to copy paste into the chat the GitHub page. So if there's a typo in terms of maybe a script doesn't work or something like that, you want to correct it, you can just go ahead and directly make a pull request or edit it within the GitHub for the tutorial. I'm also going to post that in the Mattermost as well. So again, we can just navigate to the directory we want, grab a file using that, and get something for the next step of the tutorial as well. Okay, so finally, rather than downloading the files directly, we can also, within our root macros, just stream the files if we're in EIC shell. So if you're doing this on a local machine, you can't do this, but for example, if we're running on the farm as I am here, I could write my macro such that it says, open this file when it runs the macro and says, okay, I'm just going to look it up from that repository and grab that. Where again, we just plug in where it has path to file, whatever particular file we want to look at, something .root, and run it within there as well. So we can do that. I think from the previous tutorial in January, Wouter had a nice script which kind of added a bunch of these to the chain. Maybe post a link to that in the Mattermost later. So if you want to do a lot of files, you could, if you're doing it within EIC shell, stream a whole bunch of files, add them to some analysis chain and run them, which in terms of maybe full production or full analysis is something you want to do. As we'll see from the file we've got, it doesn't contain a lot of files, or a lot of events rather. So for a kind of more full analysis, you probably want a lot more files. Okay, so just a quick reminder, and kind of going forward, so we will need a file. As I say, it doesn't need to be this one, 001 specifically. I suspect because I've been kind and given the full path for this, it's going to be popular, but it can be any file within this directory that we can grab. And I say it could, to be honest, probably be anything, just that the output you're going to get isn't going to match what everyone else has. So to make life easier for yourself in terms of debugging, I would recommend getting one of these files. I say it doesn't need to be 001, could be 002, whatever, it doesn't really matter. And if you don't want to dump it in your current path, you could change this to whatever you want as well. And if you're doing this within the EIC shell, you can also as well just take this path and you could start streaming that file later as well to analyze. That should work okay as well. It's just going to mean a modification to some of the scripts a little bit later on as we see them. So I'll give people a few seconds to do that, and I'll just point out. So again, if we're analyzing a whole bunch of files, you could stream them, and I'll maybe add that case to the tutorial afterwards as well. But if you're running it maybe locally, for example, you might want to grab a whole bunch of files and copy them and then run them. So there's a few different kind of examples of how to do that here. So I'm not going to go through this, but if you're coming back to this later, you've designed your analysis script, it runs fine, you've tested it on one file, and as I say, there's not really that many events in a single file. You want to run a whole bunch. To get them all, you might need to use something like this below. So as we've seen, with both of these methods for browsing the file storage, there's quirks in the sense that I think wildcards don't work as you'd expect. So, for example, by wildcard, I mean, of course, if it had said star, just give me everything that kind of matches anything following the star, right? So, to give a better example of that, say I want to look at anything in here which ends with .root, I could do star.root. See if anything's there. And indeed, there's a bunch of files with .root. So we can't use wildcards in quite the same manner within these different XOR DFS and MC. So there's just some examples of how you can utilize that to grab a whole bunch of files matching some specific pattern there as well. I say for the tutorial, doesn't really matter, but if you want to come back and look at this, it's there for reference as a kind of method for grabbing a lot of files. For now, all we need is this. So make sure you've done that, and then we can move on to the next step. Okay, and then at the bottom is a set of key points. So there's each of the different stages of the tutorial has this. And here really all we're seeing is different ways to access files, how we can grab them, and how you can insert them into your macros and stream them if you're using, for example, just a root macro. Okay, so question regarding access multiple files. So I think that would hopefully be answered by, as I say, Wouter had an example from the January meetings on streaming a chain. So I can, as I say, I'll upload that to the GitHub after as if every example. Maybe what I can do is I can copy a link to that for you into the Mattermost as well. So see how successful this is. That's the one. So that's a quick kind of example of how to do that. I'll also post it in the Zoom chat as well, I guess. Yeah. To emphasize though, for the purposes of the tutorial, we definitely won't need to do that. If you get your analysis script up and running, it might be a nice next step if you wanted to analyze a whole bunch and see what a huge bunch of those files looks like when you analyze them with your script that we'll hopefully make by the end of this. Okay, so the next step, now that we hopefully have our file, and as I say, from now on, we don't necessarily need EIC shell at this point. We've got our file, so in this case, favorite thing within the EIC shell, LL doesn't exist. We have our file, which in this case is this Pifia 8 MCDIS, blah, blah, blah. Huge name file, but it's the root file, and we can open that and access it. For the rest of the tutorial, I'm not actually going to be using EIC shell. I've got this thing locally to save the pain of X forwarding. So again, within this directory, we have that file there as well, and we can open it, which we'll do in just a minute. Just a few things before that. So when we look at this file and we start looking through this and browsing information, for these reconstructed files, these are produced by the output of EIC recon.
You might want to actually explain what the file name means, because all of it has meaning.
Yes, that's a good point. So yeah, so in this case, Pifia 8, this is the process in the generator. The 18 on 275, this is telling us that we have 18 GeV electrons on 275 GeV protons. In this case, I assume not many people are looking at other ions. With minimum Q squared of 10, beam effects on a crossing angle of minus 0.025, so 25 milliradians, high divergence beam configuration, and in this case, this is file 1 of that, and it's being processed through EIC recon, and as we'll see in a second, it has a lot of information within it. So Collier's point's good, because what we'll be looking at, when we start looking at, for example, the MC particles, some of the things we should hopefully see include that incoming electron and incoming proton. So we should have particles with roughly those momenta somewhere in the file, which we can take a look at as well. And also we have minimum Q squared, which is going to affect where we see the distribution of the scattered electrons as well. So that output, though, is generated by processing that input Pifia file through the simulation, through the detector simulation. In this case, we saw it was at the Crater Lake. That was the detector config. In this case, presumably after generation, that file was afterburned. We added beam effects into that as well. We ran it through the simulation, ran that simulation output through EIC shell with certain flags on, certain factories and algorithms turned on. So one thing which we will include at some point, I think, this tutorial and hopefully add, we're going to see a huge list of branches here. All of these are related in some way to something in EIC recon in terms of the factories and algorithms you had enabled when you do the analysis. So in terms of what's in there and explaining the tree, to take a look at where that's generated, you really need to dive into ESE recon. So one thing I would encourage you is after the tutorials on the algorithms and factories, take a look back at this tree and start to see if you can figure out where some of these things were created and what was fed into them basically as well. So a quick explanation as well as to why we're using a slightly older file. This is mainly due to me being too lazy to update my Linux distribution on my laptop, but that's a different issue. So the newer files and newer versions of ESE shell are using a very recent version of root 630.02. This seems to have some major issue in terms of backwards compatibility, such that if you open a file generated root 630 with any previous version of root, you have a lot of issues. So to avoid that, I've just picked a file before that change was made in ESE shell, and I can happily analyze it on my local machine, and it doesn't cause problems. Another issue as well, so the reason I'm now skipping to the local machine is that we're going to be looking at lots of plots, opening T browsers and playing around with branches. So I don't want to sit and wait for a window to be forwarded from Jefferson Lab here to Geneva and then sit and look through it. It's just going to be painful. So it's just going to be a lot quicker and more responsive there as well. So if you're running ESE shell on your local machine, this shouldn't be an issue. You can just open it and browse it happily. You could also, in some cases, this might be useful. You can use the web viewer here. So you can open this and you can select a file and take a look at it as well. So we could, I don't know, this is a geometry file, so it's a bit different. We can open it and take a look. And one of the few reasons you might want to do this, you can't really do much detailed stuff here, and we'll see that in a second. But you might want to do this just to take a quick look at a file. In particular, something like detector geometry, it's kind of nice to just open and take a look at what things actually look like. So that's available and you can use it. I would probably recommend just trying to make sure you can open this in root and browse it with root though. So it'll be a lot easier and you can do a lot more with it. Okay, so the meat of this really is, now that we have our file here, open it and take a look at the branches that are there. So we can go ahead and do that. And I think once we do this, I'll give people 5 or 10 minutes just really to have a browse, see what's there and see if they can make sense of what is there in terms of trying to find something. So a bunch of errors, which I'm not really going to worry too much about, but we open this thing. It's not showing. Is it up there? Oh. I'm going to have to stop sharing and reshare so we can see, hopefully, that Zoom window. Oh, great. Sorry, some Wi-Fi issues on my laptop for some reason now. But nonetheless, if we open that root file, if you do that, just try opening it. As I say, if you're within ESE shell, hopefully it'll work fine. Or if you have it just externally on a computer, if you just do root and then the file name, or if you need to put the full path in, if it's somewhere else, you should then be able to open it and take a look. Okay, it looks like we're going to be back in action in a second. Screen sharing. Okay, there we go. So, unfortunately a little bit small, but we can see that when we open this file, that's the file I've opened it in root, we have the metadata, .io metadata sitting there as well, and the main tree which we want to look at, the events. So all of our events are within here. And then we have, as I say, a huge range of branches with different information on different detector systems, different collections of objects, and so on. So, as I say, take a bit of time, browse it, but just as a quick example, for example, B0 ecal clusters. So the branch name, basically this is telling us that it's the B0 detector, the electronic calorimeter of that, and then the clusters that's generated. And then within that, we can see branches, such as, for example, the energy of the clusters within that detector. And if we double click one of these branches, we should auto-generate some histogram, and we can take a look at that and see what it looks like. So take a little bit of a look around, see what you can find within here. There is an exercise. I'll also set an additional challenge to that as well, but take a browse, make sure you can take a look at this, plot some stuff. We'll discuss after a few minutes a kind of different way of looking at this and a different way of taking a look at some of these plots as well. But I'm not exaggerating when I say that there's a lot of information here, and it can seem quite overwhelming at first. But a lot of the time, we're going to be looking at very specific sets of things and very specific branches and trees within this. You might want to look at specific detector systems. You can start to try and pick those out, see what's there, and what kind of information you have with them as well. So take a few minutes, browse, and then we'll move back to our exercise and take a look at a little bit of a different way of looking at some of these objects as well. As I say, typically, you can just grab one of these, double-click the branch, and then double-click it, and we can draw something for it. Well, it'll auto-generate some histogram as well. So if you're not so familiar with root as well, all I've done with this is I've opened the file, maybe just close this and show it again quickly. So within that directory, I'm sitting within this EA Epic Tutorials directory, and I have that file. I can just do root, that file, and then I can just do new T browser. I don't even think you need the new, you can just do T browser. And then this brings up this interactive browser where we can just look through and start looking at the file there as well. Okay, so as I say, I'll give people a few minutes. If you have questions, if you want to know about a specific thing, or you're confused about what a specific branch is, drop it in the Mattermost or Zoom chat. Hopefully we can answer. As I say, most of them generally are, it's some collection of objects or something from a detector, and you can start to see what it is and take a look at it as well. For example, like B0, or we might see, the end cap or something like that, and we can start taking a look at things there. This one here, it's fine. As mentioned here, in addition to kind of branches for specific detectors, some are combinations of information from various systems through, for example, reconstructed particles combines different things, different detectors, and reconstructed charged particles combines track information or things like that as well into the tree, into the branch rather. And as we'll see in the next part of the tutorial, when we're writing a macro, there are also branches which kind of encode the relationship between different things. So for example, our truth information or Monte Carlo information, and then the things we actually reconstruct. So in terms of browsing this thing, as you can see, as we go around this and we start clicking on things and taking a look at some objects, it will generate histograms automatically, and a lot of the time, that's great. It does a decent job a lot of the time in terms of making a plot, but there are definitely a lot of cases where it will give us something which is nonsense, and maybe want to take a closer look at the histogram or do something with it as well. So for the rest of this, I'm just going to quickly focus on this MC particles branch. So for example, we could draw a histogram of this, and we could look at, for example, for our Monte Carlo particles. So this basically contains our truth information, what we fed this thing to begin with in terms of that event generator, and so on. And we can take a look at that and see what is in there as well. And we could click, for example, this is our PDG. So it's going to tell us the PDG codes of the particles that were fed in, basically, into the simulation and reconstruction. As is, great. We can see we have some histograms, some distribution. it's automatically scaled this, and as I say, we can see everything on it, but it's maybe not necessarily that useful. We can zoom in on it a bit, and start to try and maybe pick out some things, probably a proton there, for example, but not necessarily that useful. However, we don't have to live with Root's auto-scaling or auto-selection of this, and we could actually make histograms and fill them with some of the information from this on the fly, which is what these extra instructions here are all about. So to clarify this a bit, I'm just going to quit Root so we don't have the T browser floating around. But what we can do is we could just draw certain branches of that, for example. So if we open our file, we could just say within the events tree, so we specify our tree here, we can just say draw and then some quantity. So in this particular case, I'm going to say draw the Z momentum of the MC particles. Go ahead, plug that in, and straight away we get that distribution. So we have the Z momentum of our truth particles coming into this thing, which again, in this case, when I plug this in, it's just auto-generated a histogram and scaled it and filled it appropriately. Useful, we can see some information from this, which is, we'll go back to that in a second, but kind of instructive to begin with. But we can do a lot more of this in terms of browsing it, and we can, for example, define and fill a histogram kind of on the fly. So we could, for example, run this command, which is again going to just take that Z momentum, but it's going to fill a histogram which we've defined, H1, which in this case just has 100 bins between 0 and 100. So we're going to zoom in on this region here, 0 at 100, and see what's within that. Might not necessarily be the most useful region to look at, but we can go ahead, plug that in, and we see, for example, straight away this object. And we could do something similar with the PDG, where before we saw that it just generated some range which was not that useful. But we could plug that in and say, actually, just give us, minus 2,500 to 2,500 in 5,000 bins. And then we should see individual PDGs popping up then, can start to identify those by comparing them to the PDG and figure out what's in that sample. So, I'll say, straightforward. We cut some of our data out. We don't have those things that were sitting at the edge, which were quite important. But for example, we could take this a step further and redraw that with slightly more sensible binning. So let's actually just do that, the same binning there. So we're going to do, in this case, 360 bins, so 1 GeV wide bins from minus 60 to 300, and see what we get. So in this case, we have a full distribution. Worth pointing out, so as Collier pointed out, that file name told us something about what we're looking at. It said, 18 on 275. So it's probably not going to surprise you that we indeed have something which has a momentum of roughly minus 18 GeV going in the negative Z direction. So that's probably our incoming beam. And on the other end, we had something going with 275 in the Z direction as well, which we could reasonably guess is probably going to be our proton coming in there as well. So those are basically our beam particles, which are there, and it's nice we can kind of identify them based on what we know about the file before we go into it. So that's great, but we can also do something even nicer with this, as well as kind of just defining a histogram and filling it on the fly. We could also apply cuts to that file based upon other quantities within the tree. So we can put some selection criteria for this and start taking a look at, for example, let's have a look at this plot, but only for the negatively charged particles. What is the Z momentum of the true particles, that the MC particles we generated, the negatively charged ones? What does that look like? So we could plug that in and draw it and see what we get. And we have something that looks like this. So as I said, we kind of expect that 275 peak was our incoming proton beam. That's gone. And what we're left with is our negatively charged particles, where happily we have a big spike at that incoming electron beam there as well, which is nice. And we could also keep stacking this up. So we could also say we want to cut on those negatively charged particles, but ones with a mass greater than 1. So we can take a look at the heavier negatively charged particles things as well and see what we get. In this case, all this number is telling us is basically how many events are actually left in there. So we see there's 333 left. We don't have very many heavy negatively charged particles sitting in this file floating around there as well. We can also, as well as this, add drawing options. So if we want to take a look at what that looked like as a histogram with error bars. What have I done wrong here? It's just an extra copy paste line. Stick that in, see what we get. So again, there's negatively charged particles where this time I've drawn it as a histogram of error bars. So if we zoom in, we see there's a bit of fuzz on the top of these things as well, where the errors are drawn on the object as well. So we can stick the drawing options in to this, and we can also, so in terms of looking at, for example, correlations between things, as we'll be doing in the next section, we might want to take a look at 2D histograms, and we can, again, draw those on the fly as well, where in this case, we're defining a 2D histogram with 40 bins in the x direction going from -2 to 2, 360 in the y going from -60 to 300. In this case, the ordering of this is a bit confusing. I never really like the way it does this, but in this case, this is the y object, and we have this colon basically then saying after that, the other object is the x. So we're going to draw on the x-axis the charge of the particles, and on the y-axis the z momentum of those things. We can take a look at the distribution of the momentum based upon charge. And we're also, again, giving it the draw option, call z, so it's going to draw it in a color scale for the log z-axis. So we see something like this. So we see our different charged particles, and again, we see basically that we had those ones with -18 sitting down here. I'm going to set a log z scale on this as well, just to make it a bit clearer. We have our basically our electron beam particles here, negatively charged, -18 GeV. And then the other side are positively charged objects. We have a big spike at 275. Again, our proton beam coming in as well. And then some distribution of other charges throughout there as well. You can see what things it's reconstructing. That's a good question. Yeah, for this file, I'm not so familiar with this particular generator or this file, so I'm not actually sure exactly what they are. I'm assuming maybe it's.
I mean, this is -1 could be quarks, but
yeah, that's the only thing I can actually think of in terms of fractionally charged things. Doesn't really make any sense otherwise, right? But yeah, I'm not so familiar with this generator. I assume it's maybe just the input is it's a quark or something. I guess we could look up the PDG for them as well and figure it out, right? But because again, we can plug in whatever we like here in terms of these axes or what cut we have. There might just be some junk object or nonsense as well.
why don't you just do it?
Plug in as PDG, yeah, as the other axis. All right, let's see, we'll do 5,000 minus 2,500 to 2,500. And I'm just going to do dot PDG. This is the trial and error part where I can remember if it's a capital. Just as it's getting exciting. I should have checked if it was lowercase or uppercase PDG before sharing the screen again. Okay, so we're changing that. So all I've done is change the y-axis in this case is now going to be PDG. And I've set basically -2,500 to 2,500 should span basically our range of different particles and see what we get there. So we can go ahead and plug this in, and hopefully I've remembered that it's the right case. It's probably going to be uppercase, I can't remember. Okay, so solution to this is a nice example as well. I can't remember the name of it, so I'm going to open the T browser and see what the thing is. Damn. It's disconnected on this. Okay, so to kind of talk through this as I'm doing it, all I'm doing as I'm waiting for the Zoom thing to reconnect on the great Wi-Fi in the room here, I'm opening the tree again, I'm opening that T browser, and I'm going to go and find the MC particles branch, because I got an error telling me basically that, there we go. I got some error telling me that mcparticles.pdg doesn't exist. So I must have misremembered the name of that, which is clearly what's happened. So I'm going to go through this, find MC particles, and indeed it's uppercase. So it's capital PDG. And hopefully when we do this time, it should draw that nicely and we should see what's going on with this. So maybe overbin slightly, but we see basically those fractionally charged things seem to be sitting around here. So let's zoom in on those.
Set projection Y.
Yeah, we could do a set projection Y, and then also I'm going to close this and just redraw it without the T browser as well, actually. And just look at the PDG. Yeah. For charge, yeah.
Greater than 1. That's the one that's
yeah, let's do that. Again, we can do this on the fly. So I'm going to do MC particles, and I'm going to say try to think of the best way to do this. Charge. Let's do greater than 0, but less than 1.
No, do greater than 1. That's the weirdest one.
Ah, okay, let's try that then. Ah, yeah. We'll zoom in on this a lot. So there's a couple of these objects which have charge greater than 1. So we have PDG codes there. So that is, let's just do, we know what the range is now. Who's in charge of this sample? Try and think what this is. That's.
Isn't that a neutron?
Let's have a look. What is that? So that's the 2212, we think. You can draw this slightly condensed range. Again, with the joy of doing this on the fly. Let's just do this as 200 bins, 2,200 to 2,100 to 2,300. 2203 and 2224. 2224.
2203 is a die core.
Yeah.
So this is probably some weird stuff, some weird intermediate during the.
Yes, that's generating some intermediate step of that.
The status of none of all of these should be.
Yeah. So indeed, that's one of the other things in terms of generator status. And things like that, when we actually go through to, is this something that we actually end up detecting, or is it a stable particle and things like that, we can cut out through other means. We're browsing this thing at quite a raw level at this point. But a nice demonstration that we can just dive in and check these branches on the fly, see what's there, and draw them in a way which, for example, as we say, when we just double click that thing in the T browser, we just have some smear of stuff in histogram, which isn't that useful to take a look at. So doing it like this, seeing what's there in browsing is quite a nice way of taking a look at it. So let's go back to the last one. Yeah, in terms of 2D objects, a lot of the time sticking log scale makes it a bit clearer to see what's going on for this as well. Okay, so with that in mind, take a play around with this as well. So you can do this, and again, it doesn't need to be the MC particles branch. It could be whatever, as long as it's something that exists in the tree. It can be some branch. You can draw it to a histogram. So again, this is just some 1D histogram with number of bins, low, high, and you can also do all of the usual stuff you would do in terms of defining a histogram and route. You can name the axes and all of that sort of stuff as well, if you want to make it more readable, which, to be honest, in the case of 2D histograms is kind of useful because, yeah, the order of these is counterintuitive, to be honest. Okay, in terms of the challenge, in terms of what to take a look at, with these tools and with this kind of stuff we've looked at, try plotting some stuff. And one of the things, for example, to look at the cluster energy of the negative n cap ecal. Can you, from that, detect a scattered electron? And again, you can start applying some cuts, for example, to that as well, where you could say, okay, based on what's detected, you can look at reconstructed particles and stuff like that as well, and say, what is this? What am I detecting here as well? What energy do I get? And you can also, again, of course, plot this as a 2D histogram as well. You could plot, for example, that cluster energy versus charge or something like that for the events from reconstructed charged particles, or maybe cluster energy versus a momentum. Play around with it, have a look, see what you can see with that as well. So identify the relevant branch and see what you can get for that as well. And you can use all of these tools in terms of drawing directly from the tree, using the T browser, and things like that as well a bit. And of course, if you have any questions, to drop them in the chat or the Mattermost in terms of what branch, or of looking at this doesn't make sense. What is this object? Things like that. Anything like that, drop them in the Mattermost in the chat, and we can hopefully try and answer it and explain what's going on. Oh, and I guess again, so if people aren't familiar with root, we can just type .q and it'll quit and we can get out of there as well, which we'll want to do for the next step. And again, something that you might want to do and take a look at as well, not necessarily in the tutorial, but later, is we're looking at a particular file. I'd say it's not actually a channel I'm so familiar with. I'm usually used to dealing with exclusive events. You could grab a different file and start taking a look at that, where again, you'll hopefully see some of the same stuff there. You can browse it and start to compare, well, for this set of events, how do things look? And again, for example, one of the first quick things you can do is when you get a file, check to see if you can see those beam particles coming in the MC particles, because in the file name, it should tell you the beam energy combination you're using, 5 on 41, 18 on 275, whatever. It should be then, you should be able to pick out, okay, there's the electrons and there's the protons coming in. I'm also going to add a little thing in the Mattermost. So I'm going to add a little thread. So just if you get something, or you want to plot something, if you get the end cap energy, just reply to that thread, and you can put your plot there, and we can take a look at what people are getting. You can screenshot it, or also within root. Just going to open this up, and let's just draw that. You could just do file save as, and dump that thing out as a PNG or PDF or whatever, and stick it there on the Mattermost so people can take a look. And again, for the next step, I'll do a similar thing where I'll put a thread up for, we edit this. So I'll put another thread up for part 3 when we're starting to look at an analysis script. People can start posting what they get out from it if they get through the exercise and get some result out from it as well. So take a few minutes, try and plot some stuff. Let's say the exercise is talking about this end cap, so if you can get that and plot that, that'd be great. Or if you just plot something else that you think is interesting, say those diquark objects were intriguing you and you want to plot them, something like that, that might be nice as well. I also assume, so from that plot, I assume we also had some of the negatively charged stuff was the diquarks as well, but going the other direction. So as people are browsing as well, quick comment on this. So as I say, the T browser generally does a good job. But for example, if you have an inventory which maybe has some error flag in it or something which has an extreme value, that can really throw off the auto binning of the histogram. So you might kind of have a load of events saying some very extreme, negative 10 million or something is the value of things which have this error flag. But if you then auto scale it and try and auto bin it with some objects which have a real value, it will try and account for all of those objects in minus 10 million, even though the rest of your events might be spread from, 0 to 1 or something like that. So the plot you'll get out is nonsense if you just double click on it on the T browser, which is where this comes in, where you can actually just say, okay, what's actually there in that range that you care about. All right, cool. So I can get some plots in there. Yeah, it doesn't. As I say, it can be this particular end cap plot as well. You can go ahead and do that. Could maybe focus in on, say, you want to take a look at the beam energy, pick out those beam electrons, plot their maybe XY momentum distribution or something like that. Verify that the beam effects are actually on. Something like that might be nice. So go ahead, try and plot something. We'll maybe give it till 9:55 Cern time. So another 2 or 3 minutes, and then we'll move on to the next part, which is making an analysis macro and really writing something to analyze this in more detail as well. Just to kind of wrap up quickly. So this is a quick comment as well in terms of browsing the file. So for the next stage where we're writing our macro, we're probably also going to want to browse this and pick out the kind of branches and things we want. So a few maybe other quick tips in terms of browsing the tree using the T browser. So we can use this little funnel thing up here as well to filter out things. So for example, say we just want to look at that MC particles branch. We can just go in there and type in MC particles, again, hopefully get the case right, and then end it with a star, so a wildcard, which will basically then just condense this just to the things which match that. And we can just see, rather than that huge kind of quite intimidating list of stuff, it just cuts us down to that as well. So for example, one of the things we'll be looking at in a second is reconstructed. This realizes me being able to spell. We're going to be looking at reconstructed particles. We could plug into that as well, for example, reconstructed. And it will give us only the trees which match that in their name as well. So rather than having, still quite a large list in this case, but rather than having that huge list of things, it's only just giving us, reconstructed things which are bring together a bunch of different things. And we'll be looking at those in a second. And of course, we can do a lot of the things we did here in terms of redrawing the plot a little bit, but so for people who aren't so familiar with root, a lot of the times we're going to be dealing with histograms. The information is stored in trees and branches, but when we double click this thing, it's kind of creating on the fly some histogram. And actually here is a great case of it doing a terrible job of auto scaling a histogram. So I've just done reconstructed particles, reconstructed charged particles, even, and clicked energy. And we have on this a plot which goes from 0 to 18,000, but it's auto-binned it to that because presumably there's some value out there it wants to try and incorporate. The problem is that because this is a histogram and it's binned, even though we can zoom in on this, the kind of damage is already done in the sense that it's already binned this in a certain number of bins in some range 0 to 18,000 or 20,000 or whatever it was. 100 bins. So unfortunately, if we zoom in on this, that's all it's ever going to tell us, that we have, in this bin of 0 to 200, or 0 to, I guess that looks like 1900, so presumably it's 19,000. So we have a bin of 0 to 190, and almost all of our events are sitting in that bin. That's not useful at all, but we could, for example, redo that and redraw that with, it's not even apply cut, we don't even need it necessarily. Let's just say I only want to look at 0 to 200 in this object, and it was, happily it just tells us the name of it as well. It's all reconstructed, charged particles dot energy, and I've probably typed something wrong there. Yeah. So now we have something which is a lot more usable, and indeed, actually, most of the stuff is not in that higher range end, but it's somewhere down here. And again, we probably actually want to zoom in on this again, but clearly already we can see that this is a lot more useful than just one bin of everything from 0 to 200. So yeah, do be careful when using the T browser. Just double click and examine things, because if it gets it wrong with the auto binning, it gets it very wrong, and you'll have something which doesn't necessarily make any sense or isn't very helpful at all. But that's just a function of the fact that it's making this into a histogram, and it is a kind of a cautionary tale, which is something going forward to keep in mind as you're defining histograms. Think carefully about what a sensible range would actually be, and also in terms of the number of bins, what would be a sensible number of bins. And you keep in mind that in this case, we're going from 0 to 200 in 200 bins. Each bin is 1 GeV wide in this case, which I'll say actually, since most of our stuff is condensed down here, we might want to modify or change slightly. Okay. So with that in mind, I say if you have a plot, you have something you've made, please just feel free to put in that thread. Just reply to that thread with your plot. And to kind of summarize this section, again, just to recap, do come back and take a look at this after you've gone through the tutorial on algorithms and factories. I say there's a huge number of branches in there, but all of those are being populated from, for the most part, EIC recon, where it's saying, I'm generating this thing, I'm reconstructing the energy in this detector and plugging it in here, or here is the cluster or something like that. So once you've done that, take a closer look at the file and then start to look through that and see if you can figure out which factory or algorithm populated a particular branch. Is it Mattermost or?
There's a question on Mattermost about how was the tree branches filtered again?
So that's here. The tree branches are filled effectively from EIC recon. So it will take the information it gets from the simulation output, use algorithms and factories to process that, and then populate these trees. So this is something hopefully we'll be adding to, probably in the extras or different kind of directory here, but some information basically about which trees correspond to which factory or algorithm, because that isn't necessarily documented anywhere as such. I mean, correct me if I'm wrong, but I don't think EIC recon has some big master directory or dictionary of this branch is populated by this factory or whatever. But you can go through and start to take a look at that. And as I say, once you've had a look at that tutorial on algorithms and factories, come back to this tree and take a look at it and see if you can start to identify that. Okay, the big summary here, though.
Can you pause for 1 second?
Yeah.
Alan, do you want to unmute and ask your question directly?
The filtering. Okay, yeah, I can show that again. Okay, so if we open the file, open the T browser, it's a little bit finicky, but if we open the file, select the tree, we can then just use this filter content button here, so it looks a bit like a funnel. It starts with a wildcard, but then we can just type in whatever we want. So let's just say, I'm cheating by just picking a name. Say I want something which matches that. I end it with wildcard, so it's going to give me anything, hopefully, any branch that matches this anywhere in this content. And we do that, and indeed, it just gives us those B0 ecal clusters there. And then we can go through and browse it. The annoying thing is that to change that, we need to click back to the events tree and then change that filter and then modify that. If we get rid of everything and just put star, it'll show us everything. So in terms of browsing the tree, I say because of the amount of information there, you might want to start looking at that. I mean, taking a look through and seeing what's there to begin with is nice. But if you have a specific thing in mind, so maybe let's just do an example where try end cap. We just put end. It's going to match anything which matches that. Now we know the nomenclature in terms of how it's structured. We could put, end cap or ecal end cap or whatever in here as well. Say we wanted hcal. We only want to look at some hadronic calorimetry. Guess we hate leptons, but we could just plug in hcal. Oh, nothing actually matches that. Probably a lowercase c. Yeah. And then it's just going to give us anything which matches that. Again, the annoying thing is that you kind of need to click back to that and then click the filter again, or else it starts trying to filter the tree you're on. Although that can be useful as well. So say, for example, we only care about stuff which features energy in here. Let's just do that. Yeah, we can filter that branch as well. Okay, has that clarified it? Cool. Okay, so to summarize this, yeah, the output trees are, as we've just seen, very dense with information. There's a lot there. That's all coming from those factories and algorithms. So come back and take a look later. But when you get your file, say you're starting a new physics analysis, grab the files that you think are relevant, take a look, explore what's there, and then kind of carefully think about, okay, well, what do I actually want to try and get from this? And then what kind of branches might I need to get that? What information do you need? What detectors do you need to focus in on, and what do you want? The Monte Carlo particles, the MC particles branch, holds information on generator level particles. And typically a lot of what we're doing sometimes is comparing, what we get, what we reconstruct to truth. So almost certainly the MC particles branch is one you'll be using at some point and taking a look at as well. So that really holds a lot of important and useful information, and is always a good starting point, as I say, for example, and really checking that, did you actually use the beam energies we thought you did, for example? It's something you can quite quickly verify by looking at the MC particles branch. Okay, so the next part is bringing that together. So, doing that from the T browser, very nice, very useful in terms of picking out a certain thing. But clearly we can't really do a kind of full analysis like that. We can't kind of say, I want to pick out this selection of particles, apply all of these cuts, do some other stuff to it, manipulate it in some way. I mean, we could do it bit by bit, but it's going to be painful. And typically what we're going to do is write some sort of analysis script or macro to process the tree. So whilst all that other stuff is useful and definitely recommend it, probably you'll be doing a lot of that in this tutorial while trying to write the exercises as well. We'll write a script, and in terms of reading these output trees, they have this pod.io output where effectively they're flat in the sense that there's no event class structure that's embedded in there. And we don't really need anything kind of additional to handle the output. It's not some very specific format or anything like that. It's just a standard root output, which you can analyze in a few different ways. We're going to look at a few examples. I'll briefly cover each of them. What I would say is that the two main ones that are included here are analysis using root directly and root using a T2 reader method. If you're more familiar with C and C++, this you'll probably find fairly straightforward. There's also a Python-based method which uses pyroot and uproot to kind of look at these. Basically, all that's going to do is take the root tree, take some of those branches and convert them into an array, which we can manipulate in the same way you can manipulate arrays in Python and do what you want with them, basically. There is also, at the end, an example which Simon's kindly provided, which uses R data frames. It's a more kind of modern method, I guess, of looking at this, and again, is something people might be more familiar with in terms of data frames from Python, for example. Different way of doing it, again, should all give the same results in the end. And also, as kind of found out yesterday, you can actually just directly use pod.io and analyze them like that as well. So that's the one that's maybe least developed. If you want to, I'd probably recommend if you want to take a look at that, take a look at it afterwards. Don't try and use it today to try and kind of analyze the file. Wouter had a few examples of that in a talk yesterday, so it's something else you could look at as well if you really hate root, basically, because both of the methods, the main methods here, really use root in some way. I guess the data frames does as well. So I'll briefly skim over each of these and kind of show an example of getting them started. But in terms of this task, this is really more focused on, we'll have an exercise with two different exercises using those files we got earlier. And really it's a case of, pick whichever method you're more comfortable with. You might be more familiar with Python and just want to use the Python-based method. Or if you're new to both, take a look and say, okay, I think actually I want to try using that way and see what we can get with it. There are scripts and kind of snippets of code which can build up. I would recommend that you try and build these things up just in terms of, take the code that's in this bit of the tutorial, write a file with it, and try and get it to run and analyze the output like that. If you get very stuck, there is at the top, if you go to the top of this thing and go to extras, there's this exercise scripts directory, which has a full script which will get you started. Basically, it combines all the little snippets of code that we have into a code which you should be able to kind of copy paste with the instructions there and get started. But I do recommend you try and kind of build it up yourself so you get a picture of how you kind of construct these things and make sure you're putting things in the right order and so on. So we're going to take a look at two methods. I'll skim over each of these. So the first method is to use T3 reader. So this is basically a root-based method where we open up our tree and we start analyzing it in some way. So quite straightforwardly, we can just, for a lot of these, we're going to need to open some file. So all I'm going to do here is open up, you can use whatever you want. I'm using Emacs, you can use Vim, Nano, Visual Studio, whatever. Just something we can open and write a file, and then we can copy paste this block of text in there as well. So this is just going to get us started. This is basically the skeleton of some analysis code in root, which all it's going to do is also going to select all of this and tab it. All it's going to do is take some file, which in this case is just a blank, as you see, it just says path to your simu file. Plug in the path to your file. If you're running this script in the same directory the file is based, you can just put its path, put a relative path, an absolute path, whatever. It doesn't really matter so long as it can find the file. All it's actually going to do in this case is define and open some new file called, in this case, outhist.root. And then it's going to close both of them. Not actually going to do anything at this stage. So you go ahead, plug that in, and hopefully run. So it's a quick example of that. Oops. Because it's a horribly long file name, I'm just finding what it's actually called, so I can copy and paste it. So I plug that in, and now if I run this script, which I can do with root -l -q, just track analysis. Say all it should have done is made a new file called outhist.root, which it has, and this should be blank. So in terms of that file, though, if we open that again, trackanalysis.c, doesn't really do anything or contain anything, but ultimately what's going to want to try and do is grab some stuff from this input file, process it in some way, and write the output to this root file, outhist.root. So the way in which we're going to do that with this method is using a T3 reader, where what it's going to do is basically make some input chain and get some information. So in this case, we can copy this into here. Okay, let's follow this strictly in terms of the comments. Plug that in. So define some T-chain. It's going to use that, but we also need to say to that chain, add some input file name, which in this case, it's just in file. Plug in there. So we've defined in file as a string here. So we can say add in file to that, and then we're going to read it with this T3 reader, this object of my chain, and we're going to access some information from that as well. But in this case, we're going to say we want to define some new array, which is just an array of integers, the generator status, where it's just going to get the branch mc_particles.generator status. We could then add more. We could add an array of floats that's going to get from there, which in this case is the particle momentum. Plug that in, and then we can do something with that. So all we're doing here, though, is telling it how to access this thing. So saying that there's going to be some array of things on the tree coming from that branch, but what we actually need to do is access that in some way. So what we can do is once we've defined that, we can have some loop like this, which is basically going to go over all of our events, get them one by one, get the events, and then for each of the objects do something. So in this case, it's going to loop over each of the particles in the event, check their generator status, where we're assigning the value from the tree to that thing there as well. And we can do a lot more of it. So just a quick example, we're not necessarily going to copy paste that in. So to do it this way, and to use the T3 reader, basically what we're going to do is set up something like this. We're going to grab our file. So I'm just going to delete all of this code up above. From there. Which will be all we need to actually get started on this. And again, unfortunately, the tabbing of this is horrible, so I'm just going to select it all and hit tab. So this is actually going to be all the information we need to actually analyze this thing. But the main analysis loop is going to be below. So quickly skimming through what we've got here. So all we've done here really is just set up a bunch of readers for the kind of information we're going to need. So we're going to be looking at the MC particle information. We're going to get its momenta, X, Y, Z components, PDG code, so we can get rid of those pesky diquarks. The generator status, we'll also hopefully get rid of them. Then we're also going to get the reconstructed track information. So we're accessing this reconstructed charged particles branch, and then again, getting the momentum X, Y, Z. And finally, the one that's maybe a bit more unintuitive or kind of something we haven't seen yet, is we're going to get the associations between the MC particles and the reconstructed charged particles. What this is going to let us do is basically say that when we have a reconstructed event, we can check, does that actually correspond to this particular simulated event? So we can say, okay, yeah, that's the scattered electron from the event, and that's what we actually reconstructed and detected for that as well. So that's how we kind of set this up and run it with a T3 reader thing. We haven't actually done anything here as well. So if you've been following along, hopefully you have a file which at this point looks a bit like this. And all we need next is what we're actually going to do and what we want to try and get from this. So the task in each case is going to be the same. What we're going to try and do is look at the efficiency for particles in this event. So the tracking efficiency basically for these things. So what we're going to do is look at the efficiency as a function of true particle pseudo-rapidity. So to do this, what we're going to do is take our input file, loop over every single event within that, and then for each of those events, loop over the stable charged particles, and then try and identify which of those reconstructed charged particles were associated with an actual true MC event, basically, as well. And then from that, we're going to create and fill some histograms to take a look at that. So everything you need to get started for that is here, where you're going to define the histograms we're going to need. So you see we're defining some 1D histograms of the pseudo-rapidity, either of these things, and then ones which have a matched track as well. And we also have this other quantity. So we could basically, at this point, take this huge loop of code, not that much, and also stick that here as well, where we're going to basically plug in that. So at this point, if we run the script, hopefully we'll get some output, at least with some histograms in there as well. So each of the loops is kind of commented. There's quite a few nested loops, but each of them should have some comment. You should see what's trying to do. Probably be clearer if you see this full screen, but you can start to look at this. So you see basically in terms of the logic of that, we're looping over all events in this first loop, selecting the ones that are stable, and then within those, we're checking the PDG codes and selecting basically the charged particles we know and love, the electrons, the muons, pions, kaons, protons, and not weird fractionally charged objects, which hopefully wouldn't have passed this anyway. And then from those things, we're accessing the momenta for them. So earlier we had basically those readers where we said we wanted to get the particle momentum. We're grabbing that and we're assigning it some free vector, and then we can then manipulate that and get the value of the pseudo-rapidity and phi for that event, and then filling a histogram. So this line here is filling a histogram, which we defined above. One thing to comment, so if you're unfamiliar with a class or don't know what's going on with it, again, you can ignore this if you already hate C and root and don't want to do it this way. Basically, we could take a look and see what can a T vector free do, and just go and Google that and say Cern root, frozen again. Apologies while it connects. But basically, we just take a type of object. So, for example, a t-vector free, copy that into Google, just type, Cern root t-vector free, hit enter, and it should bring up the class reference for that as well, which, again, because the Wi-Fi is frozen, I guess it's not going to search for me at the minute. It's the Wi-Fi is disconnected at the minute, I think, is the problem. Like it's coming back. Okay. So apologies. So hopefully everyone can see that again. Yeah. So we could then go into that and take a look at this, and we'll see, for example, dot pseudo rapidity is hopefully something this class can do. Indeed, it is. So we can just access basically. So what it's going to do is take that free vector and calculate the pseudo rapidity, which is just some double it's going to spit out. Or some float that it spits out and we can use. There's then a loop over these associations, checking to see if we can match basically the tracks to the truth, gets those, and again makes some other free vector of the actual reconstructed things, and then again we can get the real value of the pseudo rapidity and so on from that, and assign those different variables. It fills some histograms, and then at the end, after all of that, we're just going to close those things. I feel like this hasn't tabbed that quite correctly, but there we go. And hopefully if we run this, it would work and spit out some result. Again, like any good art show presenter, I've already done this. So at this point, if we construct that script, we should have something which will basically give us the following output. So I've called it, in this case, efficiency analysis. This is the bare bones starting point. So if you go to the extras tab and find the exercise scripts, this is effectively what you'll get. You'll get this efficiency analysis.c script, which when you run it, will produce this output, efficiency analysis out, which is just filled with a few simple histograms in this case. So we have the pseudo rapidity of our thrown charged particles, the ones that had a matching track, and then this quantity delta R, which we calculated, which as we can see, maybe isn't binned as nicely as we could. So something to think about in terms of that. So in terms of the task, what we're going to do is, this is just a starting point, this is a skeleton. What we want to do is find the track efficiency as a function of pseudo rapidity. So what we want to do is add to this macro lines which will basically produce an output file which contains that. And what we want to do to get the efficiency is take the ratio of the histograms we've defined. So we want to take the ratio of the particle eta, particle pseudo rapidity, to the ones which match a track as well. So that itself should be relatively straightforward. To kind of clarify, we can, again, familiar, you can see what a TH1 can do, which is a histogram. And it's saying we want to take the ratio. Effectively, what we want to do is use the divide function of these things as well. So we can divide histograms where we basically take one, divide it by the other, and that should give us our efficiency, effectively. So that should be straightforward, but then there's a few extra tasks as well as that below. So after we have it as a function of pseudo rapidity, get it as a function of particle momentum instead. There's a point here as well, just in terms of a few things to think about. The histogram ranges, as you're plotting it, we've just stuck in some default values in terms of the number of bins and the range. Think carefully about that. Should you rebin them at all? Should you change that range a bit as you're doing this? Do you want to modify it in any way? In addition to that, do you want to apply any cuts to this thing? So as you're plotting this, think carefully about, well, if you're looking at reconstructed charged particles and you, for example, say you only care about the central detector, maybe you don't actually care so much about the pseudo rapidity if it's falling outside of a certain range. And this might be something you're looking at a certain set of detectors. Maybe you're not so bothered about certain pseudo rapidity or phi range, for example, and you can apply cuts. And basically the way in which you do that is put in statements to the effect of, if quantity is less than or greater than something, fill or don't fill some histogram, for example. So this is going to be the same exercise between Python and root. So we'll take a quick look at the Python version of this. And again, to kind of get started on that as well. But if you already know you want to use root and don't want to touch Python, feel free, go ahead, just start running the exercise, start trying to get basic that efficiency, and then start adding this extra stuff in. So for example, finding that efficiency is momentum, look at some 2D correlations, and plot. The final thing is to look at some kinematic distributions for all of the reconstructed charged particles, and not just the ones that are associated with a thrown MC particle as well. Okay, so I'm going to skip the resolution analysis, and I'm going to talk a little bit about the Python version of this instead. So the Python version is very similar. So again, in this case, what we're going to do, just going to make some little script called trackanalysis.py. What we're going to use here is a relatively stripped down set of packages. We're going to use uproot and array, basically. So skeleton of this looks a bit like that, where we just, again, we plug in our input file, which again, I'm going to have to go and copy the path for because I'm never going to remember this off by heart. Plug that in. So it's going to tell it, get this thing and open it. And also while you're there, open this new output file, track analysis out py.root. And in this case, what we're going to do is use uproot to open that tree and take a look at it and get some arrays from that as well. So the way in which we do that basically is by plugging in commands like this, where we're going to define the thing we want to look at. This is going to be an array of the generator status, which we can get from there and plug it in. I'm not going to copy paste these because actually there's a versioning issue of this where I have to change the text a bit. But what we do is basically plug in these things, and you should be able to go ahead and do this. And if you've been EIC shell, that should all be fine. It should all work. We basically take those branches, turn them into arrays, and then we can loop over those arrays and do some stuff where things look very similar to our previous one, where again, we're just going to loop over all of the events. So the event tree itself has a specific number of events, then we can loop over all of those with some integer I. And then within that, we're going to loop over the thrown particles, select stable ones. We're going to grab the PDG values, and then we're going to cut on that and so on as we keep going. And yeah, so there's a warning there that using slightly older versions of uproot, the way in which it accesses arrays are a bit different. So yeah, if you're using very old versions of uproot at this point, you have to access them like this. So we go ahead and do that. And again, with the efficiency analysis, the kind of next block of code we need in terms of those loops, we would also need to define histograms. So again, the default histograms are there, so this is the name of it in terms of the name of it in the root file. This is the title, and we can add X and Y axis titles, basically like this, where it has a semicolon for the axis, and it's going to plug that there as well. Although we could do that in a nicer way, as we'll see when we look at the finished examples. So define the histograms, and again, basically here's that main analysis loop where it's looping over each of these things in turn, very similar. The only difference really here is that we have this extra index to keep track of the event that we're on in each case, but the output should be exactly the same if we go and do that. So that's the rest of the block you need for that. Following that, our task is the same, where we want to get the efficiency as a function of the pseudo rapidity, and then add to that in terms of doing it as a function of momentum, looking at it 2D, and so on. So finally, there is also, again, a very similar, I'm only going to show basically this block, which basically this is the skeleton you need if you want to use an R data frame for that instead. So Simon kindly wrote this code, which we can use and run. A few caveats to running that, which are included in the tutorial there as well. So just to quickly demonstrate, it's going to run my very bare bones efficiency of analysis. So hopefully that is just going to produce that file for us, which just had those simple histograms, which when we look at it, it does. So we have the thrown charged particles and then the ones which have a matching track. So for the first part, all we really need to do is divide one by the other, and we could actually do that directly from the command line here as well if we want. But ultimately, we want to put it in the script and define some histogram, which it can write to, particularly because we're going to want to do a bunch of other stuff as well, such as putting it as a function of momentum. So at this point, this very much is a kind of play around with it, have a try, and yeah.
Sorry, there should you also maybe our data frame is in the root Python?
To add to this, you mean?
Yeah.
Easy, man.
You could do the same, effectively the same thing with Python.
Yeah, I think it would operate in a very similar way.
The example.
Yeah, this was a very last minute addition to this as well. Yeah. So I say at this point, it's very much pick whichever method you like the look of more or are most familiar with. Give it a try. As I say, you could make the very first plot from the command line, but add a new histogram, which is resolution or efficiency rather, and plug that in and just divide one by the other, and we should get our result that we need. I'm going to make another thread in the Mattermost so that when you make that, you can put your plot there and then kind of work on it and improve on it as well. And then after that, go into the next step of the exercise, which is all about plotting that as a function of momentum. So again, think about how you'd go about that. And again, what we need to do to get that plot in the end as well. So I'll put in the Mattermost quickly. So in each case, the strategy is very similar. I think even in the odd data frames example, it's quite similar where, okay, there's not this set of nested loops. But again, we need to define some histograms we want to fill and the kind of quantities we want to cut on and the cuts we want to apply. So even though I've not used all data frames before, looking at it, I can see, okay, the logic is still there. And what we're trying to do is very similar. So I'll give people 15, 20 minutes to play around with that, try and get something out, particularly the first stage in terms of getting the efficiency for the charge particles should be straightforward as a function of pseudo rapidity. Adding it as a function of momentum, we need to do some extra steps, which may take a little bit of looking into how the t-vector free works and what we can do with it. So at this point, I am actually going to take a seat. It's time turning it over to you. And I'll try and monitor questions basically in the chat for both. So have a play around, have a try of it, and say at 10:45, I'll run a quick I'll run through my solution to it in inverted commas where I have a version of this that we spit out at the end.
I mean, you could do one of these the TG reader, but I think that's what yeah, so you don't need to do
Yeah, we don't have this is a solution, but they also
TG reader.
yeah, this is tricky.
Possible to get
I know. They want
you want to read her.
yes.
I'll have a deeper look at this then to see what it's saying.
Just ominously zooming in on this, but as a hint, this is a method you can use to do that division.
You take a look at Alexander's questions online.
Yeah, sure.
The thread about classes. Beyond the scope of this tutorial.
Yes, I know. This is a deterrent for the announcement.
Yeah, maybe one. Yeah, maybe one I can discuss offline. We can chat through it after. Yeah, I think it's going to be more detail than is needed at the minute. But
What about compilation?
compilation makes it faster. That's a good point.
I'm putting together some rig of standalone compiling with the guys.
Yeah. Strictly speaking, I mean, someone ran into this problem recently where they were trying to construct some huge chain of files and run it, and they were having some issue combining the files. My answer was basically just, you can analyze them individually, and if each one takes 5 minutes and you're using a batch computing system, just make a bunch of different jobs and run them right. Again, it's something, it's maybe a slightly pithy answer, but again, if we get those macros like using Condor, which you were talking about earlier, up and running, it should just be a matter of, drop a shell script in which says, this is my file, run this macro on it, submit it, and run it for 5 minutes somewhere. I would say typically that this analysis stage, unless you're doing a lot of things or it's getting very complicated, hopefully it shouldn't take that long because the number of events you're dealing with in each of these individual files is quite small.
There are some very weird mistakes that it's not the starting the programmer and allows the compilation. It's untraceable.
Yeah.
Just logic.
That's all the fun of writing macros in root, though, right? Discovering what the hell's gone wrong with some weird pointer or segfault error. It's almost always a path issue. That's my only advice on that. If you're getting some weird issue with a root macro, it's almost always, something isn't named correctly or there's a path issue or something like that. I would say that's probably actually why I prefer root macros to the Python/uproot approach. Python is even less transparent with what's gone wrong sometimes. I'm just going to stop sharing my screen for a moment while I bring up a plot, which might be useful as well. I'm not actually sharing my screen with Binwith, so that's actually helpful. Okay, so we'll have a few minutes of playing around. I'll run through a kind of one I did earlier in terms of the pots that we get out. And I'll take a look through the script. I can show both versions with the Python and the root versions, basically in terms of the kind of completed exercises. So I will post these online again in that extras directory where it was the exercise scripts. I'll plug in there the kind of completed version of these. Probably not today, probably on Friday or something like that. So people have a chance to kind of try these and try running through it and getting something out of there as well, without just immediately skipping to kind of the quote unquote answer. And we've got a plot there already. Sorry? Is it between 0 and 1? It looks like an efficiency, yeah. That's what we're aiming for, yeah. So I guess a comment as well in terms of the efficiency, yeah. So when we're doing this, we're looking basically for some numbers between 0 and 1, where 1 would represent for that particular bin, we've detected all of the particles we threw into that bin. We could scale it by 100 if we wanted and do it as a percentage. Yeah.
One, two, three. Okay. So I would like to do all analysis in R data frames, but there are almost no material for it. So how do I deal with it?
I would say, so Simon's example works and it's a case of adding to that. I think what I'm going to try and do is add to that. That is very new because I to be honest, personally don't know anything about R data frames. I've never used them or
It's
worked
similar
with them.
to pandas in Python.
I've never
But,
really worked with pandas much either.
okay.
This is where I'm showing my age and I'm not even that old. That I'm just used to dealing with root macros and doing it like that.
Because this is like the breakthrough of the root using these R data frames, which are parallelizable and multi-threadable and so on.
I know it's the way things are going, and definitely that's something I want to add to this. Where yeah, I say that the kind of skeleton of getting started is there in an R data frame. What I would like to add is the kind of completed example for that, which is something for my own interest. I think I want to actually add and do as well. Where, so I say I've not worked with them myself personally, so it's.
Can take the exercise to just change the R data frame example there into the efficiency one. That should be a reasonably easy example. Myself. Well,
You just understood, but there are any some examples in terms of the small examples, but also
I think the problem, so the discussion in the room is a bit about kind of R data frames and the examples or lack thereof on the internet at the minute, right? They are quite a new tool, I think, and they are there basically because people are used to dealing with pandas and things like that. If they come, particularly if they're coming from a computer science background, they're maybe more used to dealing with things in this way, because I know pandas as a way of working with data are incredibly popular, right? And I think the existence of our data frames and the creation of them is a response to that, where people not in the field or are coming into the field now are starting to use them in that way.
yeah, so we have someone else in my group who is a big fan of them as well, and he guided me through the first steps, and then I just set myself a project to convert it into our data frames, and that's yeah.
I'd say that, yeah, I would say I'd like to add it to this and make sure that both examples are there with our data frames as well. And that's something I think I will try and work on when I'm back, basically in the UK, sitting at my desk. As I say, mainly for my own learning, because as I say, I know it's the way things are going, and I just want to have some example of it that works and you can use. And I would say I would encourage if you picked one of the two main ways of doing it as presented, just because you're more familiar with it, this is a nice chance to kind of try it a different way as well, since it is relatively straightforward as an example when we get to the end of it. So testing, if you run the root version of it, trying the Python version of it and seeing, okay, can I get the same result from one to the other once you've added and made your root one correct? Or, correct. Okay, so I'll give it another minute. Let's say if you've got an efficiency plot, doesn't need to be kind of the full thing completed or anything like that. Just, if you've got the first stage of it, don't even need to make it look fancy or nice in root, just kind of chuck it in the thread there when you get it. And I say, if you come back to this later, you don't get the time to finish it at the minute, but you play around a bit more later and get it. Post then can take a look and see what people get for the plots and the analysis. So in a second, I'll take a quick look at my kind of solution version list and I'll run it and we can see the output I get for it from there as well. So let's quickly, I'll look at the root version first. Okay. So starting from this, that's the one we started with. I've got, my horrible, complicated, absolute file path at the beginning here. I go through and process it. We have our things defined and so on and run through that generator. In my solution, what I've done is, in terms of the trees and things we're reading, nothing really needs to change here. We have basically all the information we need. What I've done though is define some new plots. So I've just defined basically some plot called track momentum resolution. Oops, this is the resolution, not efficiency analysis. My apologies. I'm getting too far ahead of myself. So similar thing, all I've done is basically kept the trees the same. We don't need anything new necessarily. I have changed the range of the histograms a little bit. I've rebinned them slightly. And also I've added, so we can add basically the actual Greek symbol there if we want, instead of writing just, capital E there. If you plug in this hash, you can do very latex style stuff where, for example, I could add a subscript if I just do that and then add in curly brackets some text. It would then subscript that. Or again, very latex-like, we could do uppercase or superscript there as well with it. So I plugged that in. In terms of the plots, I added a few more. So I added one, which is particle momentum. So for the second part of this, when we look at the momentum as the efficiency as a function of momentum, we also want kind of an equivalent set of plots. We have the pseudo rapidity for thrown particles and the pseudo rapidity for the matched thrown particles. We want basically the momentum of the thrown particles and the momentum of the ones that have a matching track. So I played around with this a bit, and I would encourage you, as you're doing this yourself, try it, see what that momentum looks like, plot it, and kind of determine a range which is maybe suitable. You might find, most of it is off scale or something like that when you first do this, so kind of play around with that a bit. I also added a similar thing for phi, where I've basically defined some histogram which we can fill with phi for each of those. And then within that, some extra things there as well, some 2D histograms here for the last part of that exercise, where it's defining basically momentum versus pseudo rapidity and phi versus pseudo rapidity as well. So these are defined as 2D histograms. We again have the same thing where it's thrown, so our Monte Carlo ones and the ones that have a matching track as well. So the reason I've defined both is that, again, we can get an efficiency for that by a division of the histograms basically as well. I also added some extra things. So we had in the analysis code, we'll skip to that. We had at the bottom of it, this delta R, which is comparing between the reconstructed track and the truth track, the difference between that. I added a few other quantities like that as well. Maybe it's something we want to cut on. Maybe you don't want to compare or include events where, for example, the value of the reconstructed pseudo rapidity is too different to the actual pseudo rapidity or something like that. Maybe you could use that to say, it's not a track that I want to look at. I haven't done so. I've just defined that as something we can take a look at as well. Similarly, I've done something with the momentum where I compare basically the true and the reconstructed for each. And then the actual kind of solution of the analysis, I guess, basically is the fact that I defined some new histograms, which are the efficiency of each of these things. So this is the efficiency, the track efficiency is a function of pseudo rapidity, of momentum, and of phi as well, which is maybe a bit excessive. We can take a look at it. And again, the same thing for the 2D. And then there's this last part of the exercise with these charged particle histograms where we want to just look at all charged particles. I added some plots for that as well. So our loop is very similar, except that now I also define basically these extra histograms and fill them. So all I do is fill in for example, for the momentum, I say take that free vector, the true momentum, give me the magnitude of that. That's the momentum of our particles. Similarly, for the 2D, I fill it with the magnitude of the momentum, the value of the pseudo rapidity, and then phi and pseudo rapidity as well. Very similar thing for the kind of ones that have matching track. I go ahead and fill that with the corresponding values of the kind of particles there as well. So this is the loop I use to get those charged particles. Pretty straightforward, basically. I just say, loop overall charged particles. I nest that within the event loop as well, though. So as you see here, I've added some extra things which is basically tell me what each of these closing brackets is doing. That one's ending the loop over charged particles. That's ending my loop overall event as well, just to keep track of things as we go through. And then the very last thing I do to actually get those histograms basically in terms of the efficiency, all I do is define, with those new histograms, I define the efficiency ones. I say that is the result of the division between those two things, and I get my result. So I'm not going to save it, but exit. But I've run that with this, it should hopefully run some complaints, but spat out some file efficiency analysis underscore exercise out dot root, which if I open should have all the stuff I need. Where if I do that, dive in, quite a few more histograms now than there was before. What we really want is, for example, the track efficiency as a function of pseudo rapidity. Go ahead and do that and take a look, and that's what we get. So as mentioned, though, in plotting this, you might want to narrow in on a specific range or exclude the events, for example, where we know the central detector isn't actually there anymore. So for example, here, this really is kind of going into the far forward detector region. So we might not actually necessarily want to include or plot this in our histogram as well. Although it's kind of nice that we can kind of clearly see that basically we're hitting the edge of our central tracker region. And of course, the efficiency then drops off as we kind of get to the service region and stuff like that. But for the most part, kind of up here, the efficiency is pretty good. We're talking kind of 90% up to 100% in some particular bins for the tracking. So it's doing okay. And again, that's for all of our charged particles. We could, if we like, specifically say, only give me, for example, the electrons. What's the attracting efficiency of things that look like electrons in here as well? And we could do that just by changing within that main loop when we had that. Yeah.
After your,
yeah,
just for people to analyze, you should divide it with binomial option to have a better estimate of mistakes.
Yes, yeah.
From the
in terms of actually making sure, yeah, because I mean, clearly we don't actually just have 74 entries here and stuff like that. There are subtleties within root in terms of if we want actually, for example, realistic errors on this histogram, we need to do a few other things. But yeah, and I can kind of demonstrate that quickly in the sense that the errors in this histogram are going to be nonsense if I draw it like that. Yeah, so we need to specify some things in terms of before the division of this. But for a quick look, this is all we need really. But yeah, we could, in that loop where we, for example, look at, get rid of that. Here where we say, if the PDG is 11 or this or this or this, we could just say, if the PDG is 11, plot it, and then we would only get our reconstructed electrons, for example. This is all of them, so we can kind of select from that specific things, or we could check the muon tracking efficiency, for example. The statistics might suck, so we might not get a very good answer there. And then for the momentum, we do a similar thing where I define this new momentum distribution plot where for our charged particles, our momentum distribution looks something like this. And then for our ones with a matching track, looks very similar, a bit of a drop there we saw. And also you can kind of see as well between the two, just in terms of looking at the number of entries, we have a lot more thrown than we do actually reconstructed with a matching track. So when we look at the efficiency, we're not going to expect 100% everywhere, for example. When we look at that, indeed we see, and it tails off very quickly. Again, in terms of the errors on this, it's going to be junk because the stats are rubbish, but say if we selected, again, we might want to actually zoom in this region a bit and only actually plot it in, say, 0 to 20, and looking at the track and efficiency of those things instead. But for now, that's all we can do for that, all I bothered to do for it, rather. And finally, as well, we also had some 2D histograms. So we defined those and plotted them, where, for example, that's the momentum versus the pseudo rapidity of these particles. So we see basically that our high momentum stuff is unsurprisingly going very far forward in this case, or going towards the back as we increase the momentum that way. We could look at it in terms of phi as well. look at distribution and fine, that's what we get. And then again, we did some division. Hidden beneath the start boxes are corresponding over lobe. We get our result where the Z scale here basically is our efficiency number. So yellow, the ones trending towards yellow are kind of higher efficiency and blue is lower. So again, we see that dip basically where we're going into the region where we don't have the central detector anymore. So as we might expect. Okay. I think in terms of that tutorial, so I'll maybe run and show the Python version of that quickly as well. The results are the same, but again, very similar. All I've done is define some new histograms that I can divide. And again, I've done it in a lazy way where basically I just divide one by the other. Should add some extra stuff to make sure the error balls make sense and that it has the right statistics, but in terms of how it looks, it should be very similar. So all I've done is add those and then fill some extra histograms where again, I access, for example, the momentum in a very similar way where I basically take the vector I defined, root t vector 3, from the momentum of the MC particles, and then I say, give me, you know, dot mag will give me the momentum for that, and then I can fill associated histograms. Okay, so I think that kind of brings us pretty much towards the end of the time we have. So I would say to kind of try this, start with the efficiency analysis, run through this, try and finish this exercise, and then the resolution analysis is very similar sort of plots, or in this case, all we really want to do is look at the resolution of some particular track momentum. We can go ahead and do that as a second exercise, try that once you've done it. Once you've got the efficiency, it's a matter of changing what the loop is doing slightly, adding some new variables here. You see basically we add this momentum resolution variable, which is pretty straightforward. Basically, we take what we reconstruct, compare the difference to truth, and then divide it by the truth information. That gives us basically our resolution for this thing. So fairly straightforward. Again, we can do it in a similar way where we just add in some histograms, add in these new things, and fill relevant histograms with it as we go along. And you can do that in your chosen method of Python or root or whichever you prefer. So do take a look, and as I say, the extras page, so I'll maybe end with that. Let's go to the bottom. Or extras page, there's this additional resources lesson. So basically, this is just pointing out that there's an extras tab, which has this link to the exercise scripts and the examples repository, where you can basically grab the code from here, copy paste it directly into a file, just follow the instructions, and you can run the kind of skeleton for each of the exercises. I'll post the solutions, the kind of completed versions at some point. Maybe I'll even do the division nicely. I'm not sure about that. But I can plug it in. And I say I'll probably do that maybe Friday or early next week. So as I say, at the minute, it's quite a lot of information if you're new to this to kind of just get going now. But try it, test it, come back to the thread, post the plots you get, share what you get. If you have any questions, let me know or let us know in the Mattermost and we can answer them, and give it a shot and see what you get. And as I say, the efficiency one is there. And in terms of once you've done that and you're familiar with it, I would say maybe just jump in straight away by taking that resolution analysis code, dropping it in and running it, because at that point, you know, it's very similar. It just gives you the right skeleton to start with. Of course, just make sure you put the right path to the input file there as well. And there's the uproot version, and as I say, I think personally I will probably actually try and add some more data frames versions of this as well. So keep an eye out on that if that's a method you want to take a look at. Come and revisit this in a week or two, and hopefully there'll be something there. All right, so I think that wraps up the lesson. I think we had a 2-hour time slot, right? So thanks everyone, and as I say, if you've got questions, drop them in the Mattermost. I guess the Zoom chat will be open whilst we're getting coffee.
Drop in Mattermost.
Mattermost is probably easier, yeah. It'll be more persistent, yeah. So if you have questions or problems, for example, you're running something, adding something, and it doesn't look right, drop it in there and we can take a look and try and help out. And as I say, when you get a nice plot out at the end, feel free to save it, add it to that thread and say, this is what I got. I think I already have a volunteer for a nice looking efficiency one with nice error bars, so you can drop that in when you're done, and we can have a look at that. Does it have the error bars?
No, without everything, but just have a look for people to know how to calculate efficiency.
Yeah. So indeed, once you do this kind of nicely and account for the errors correctly, you can make a version of this. So this is plotted basically just as individual points. So rather than binned, it's basically just the points with error bars for each. The width, the
Instruction is up there. All of this.
Binomial.
yeah.
Okay, it's not good.
Yeah, it's there, but basically a few extra flags to the division command. But it does that nicely where we have actual error bars for this as well. So we can say a bit more about this, and we can see basically, presumably here we're very limited by statistics effectively. All right, so thanks, and
One more note, if you still have problems installing EIC shell to begin with, please also drop us a note. We now have a bit more time to help out with that.
yeah, and that will be needed for the next lessons as well, particularly ones playing around with the geometry and the algorithms. Oh, and I should add as well, this examples repository at the minute, hopefully this will be getting populated. I've tried to break this up basically by physics channel or physics working group. So as I get them, I'll add basically examples for different scripts where you can come in, for example, once you work through these exercises, see you were working in a certain working group, you can come here and see, what exists, take a look what people are trying to do and see if you can make sense of it, and then try and figure out what you want to do and